previously we had talked about what the pumping lemma is. It is a property that all regular languages have. Namely, if L is regular, so if I give you a regular language, L, it has to satisfy this pumping lemma. And we proved it. We talked all about what it is and how you could derive it. Then L satisfies the pumping lemma. I might ask, Dan, so let's recap what the pumping lemma exactly says. But I'm going to try to do it in a way that is trying to be explicit where the quantifiers are. So I'm going to put this into two pieces, and we're going to just rip apart the logic of the whole thing. It's going to help us see what we can use this pumping lemma for, just as an example. So there exists. So notice it's an existential quantifier for those that know what that is. There exists pumping length P such that what? For all strings. So notice a universal quantifier for strings of the following form. For all strings W in the language with length at least the pumping length, there exists, notice there's an existential quantifier, there exists a way to write W is equal to the three parts, right? X, Y, and Z, such the following. Such that we had these properties, right? That Y is not equal to the empty string, meaning its length is at least 1. That the length of XY is at least the pumping length, and so these two I'm just going to lump together because it's easy enough for them to just be paired up like this. And for all k greater or equal to 0, string x y to the k z is in the language. So you might be staring at this and say, Dan, yeah, you talked about the pumping lemma before. Why'd you break it out into quantifiers like this? It's because I want to talk about something else that at first, when you first look at this, say, oh, like that's cute that every one of the regular languages satisfies the pumping lemma. But there's this thing in logic we have called the contrapositive. And it goes like this, if I were to apply it to this statement. So the contrapositive of the above statement is the following. So, and it makes a lot of sense, right? If you think about this in terms of common sense reasoning, you think, okay, L is regular, that means it satisfies the pumping lemma. What would it mean if L doesn't satisfy the pumping lemma? Remember, it's a property that all regular languages have. What does that mean? If L does not satisfy the pumping lemma, remember, this is a property that all regular languages have. So what can I say about L then? Then L is not regular. Right? Because that's a property that all regular languages have. So this is the contrapositive of this statement. So this is actually one of the killer applications of the pumping lemma, is that you can use it to eliminate possibilities of their existing DFAs, NFAs, epsilon NFAs, or regular expressions for a given language that you're interested in. So if you can show me that L doesn't satisfy the pumping lemma, then you can exclude it as a regular language. It means it's some other kind of language that we haven't talked about yet. So you might ask, Dan, okay, so what does that mean then? So what does it mean then to not satisfy the pumping lemma? So to satisfy the pumping lemma is actually right here. This is the pumping lemma. So now let's go through the exercise of negating that. So, and the reason why I did it like this is because this has a lot of quantifiers in it. There's it exists. And once you get to that part, then you're going to say for all strings, there exists a way to write it like this, such that it has this, where it satisfies this. You see, there's a lot of quantifiers, right? Let's think about this now. So this is the pumping lemma. And this is where I try to simply just take the pumping lemma. So what does it mean for it to not satisfy the pumping lemma? Well, what does it mean? Well, if it says there exists, that means that it has to not just be that it exists. To reject this claim means that I have to show you that regardless of what this pumping length is, so I can imagine I have this. So instead, what does it mean for the pumping lemma not to apply? It means for all p greater or equal to 1, there exists, so remember, you see existential quantifier, that means that you're going to need a universal quantifier to negate that. So after that, then we have to talk now about the string. That's the next part here, right? Do you notice now it says for all strings? That means that there has to exist a string. We're going to flip the reasoning here. There exists string W in the language with where its length is at least p, the pumping length, such that, now this is where it gets a little bit weird at first, is remember, it said that there's a way to write it such that it's written into these three parts, and it has these properties, right? Well, now we have to say regardless of how you could write it. So that means we're going to switch that to an existential to a universal. So here we go. Such that for all x, y, z that are in sigma star, w is equal to x, y, and z at least one condition because remember, it has to satisfy all of these, right? So for it to be invalidated, one of these has to be false. At least one condition below doesn't hold. So that means that one of the ones we have listed here has to be wrong. So one of these has to fail. And typically when you prove that a language isn't regular using the pumping lemma, usually your best friend is this one right here. Because to falsify this claim, remember it says for all, to show that this doesn't hold, because remember, universal, when I negate that's an existential claim. So all I would have to do is pick a k such that whatever I get isn't in the language. That's usually your best friend when you're proving a language isn't regular using the pumping lemma. But please note, and this is a common pitfall for students, is that you don't have control over how this string gets decomposed into these three parts. Notice that it's for all of these. Unlike over here, there exists some way to do it. That's what the pumping lemma says. Here it has to be that you have no control over that. So you can imagine this like a game that you're playing with someone, where if somebody were to propose to you, that something it doesn't satisfy the pumping lemma, so some language doesn't satisfy it, you can imagine it like a game. So if somebody were to propose this to you, you can imagine this as the strategy on the other side, how you'd refute their claim. So you can almost look at it like a two-player game where you follow through each one of these steps, one after the other, and you can see how somebody could refute the claim. Pretty nifty, right? So let's do an example now, applying this argument. So let's try using the pumping lemma. I'm going to abbreviate it as PL just to make it shorter for us. Let's try using the pumping lemma to prove a language is not regular. So we're going to establish the following language isn't regular. And I must stress that this isn't the only one. There's many, many, many of these. There's so many of them I couldn't count them all for you. So we're going to consider what I'm going to call L equals. So notice that this string always has the following form. It is where the number of zeros and the number of ones are equal to each other. So for example, a string like this, that's a part of this language, where you have equal numbers of zeros and ones. So this would also be in that language. So take note, and you stare at this and be like, really? There's no DFA for that? And the answer is, there is no DFA for this. Do you notice how the M's, they're arbitrary? If they were fixed, most certainly you could come up with a DFA for it, akin to some of the examples we've seen previously. Like if it was just that those are some constants, then most certainly you can play around with that. But anyways, here's what we're going to prove. Here's the theorem that we're going to prove now. So we're going to go through the game plan here. We're going to walk through it carefully. So language equals, or LEQ, is not regular. So let's prove that this is not regular. So we're going to put the pumping lemma into use. So proof. So the canonical best friend that you would have when you have something like this over here is contradiction. We're going to assume LEQ is regular. And I must stress, we're doing this for the sake of deriving a contradictory statement. Then if it's regular, then it satisfies the pumping lemma. Then by the pumping lemma, the pumping length, which remember, it's a constant, right? The pumping length P, as in the pumping lemma, exists. So, you might say, Dan, what are we going to do here? Okay, so remember, the statement of the pumping lemma, we have that constant, right? So now what I'm going to do is I'm going to play a little game of batting this around here. So to get the contradiction, I'm going to present a string to you, namely one that's of a sufficient length. So notice that there exists a string W with that length being at least the pumping length. Remember, now we know it exists because we've assumed it's regular, right? So now I need to come up with a string that's going to be a part of that language. But it has to be at least length P, the pumping length. Consider this string. 0 to the P, 1 to the P. Is this a part of the language? Yeah, it is. Because notice that it has equal numbers of zeros and ones. There's just P zeros, then P ones. So that's a part of this language. So remember that this is indeed a part of, so I'm just going to put in parentheses, which is indeed in LEQ. Now, remember, the string has at least the pumping length in terms of the number of symbols, right? Its length is at least P, which is what we need over here for playing this game of bat and forth, okay? Okay. So, since the length of W is at least P, what does the pumping lemma say I can do then? It says that I should be able to decompose it, right? There exists a way to do that. Now, do you note that when I say there exists a way to do it, I don't actually tell you how I can do it, right? You don't have any control over that. If we're thinking of this like a game over there, there exists a way to do it. But I don't know what it is. I don't know how it's decomposing into the three parts. So my argument has to work regardless of that. But remember, it satisfies the pumping lemma by our assumption. So we have some properties we can use. And the point we're going to get at is we're going to try to show that the string that we picked is able to pump things that don't actually exist in the language. And we're going to try to take advantage of the fact that I picked this W very carefully. So please keep in mind that there's equal numbers of zeros and ones, but also, as I'm going to indicate later for you, notice that the first P symbols are all zeros. So keep that in the back of your mind. That's going to be your best friend in this argument and the way I picked W. So since the length of the string is at least P, then by the pumping lemma, right? Then there exists a way to divide W so that W is equal to X, Y, Z, where Y isn't empty, or Y isn't empty. The length of XY is at least the pumping length. And for all k greater or equal to 0, xy to the kz is in LEQ, right? So now we're going to try using these properties that we have because it satisfies the pumping lemma to come up with a statement where it's satisfying the property, but it also isn't satisfying the properties as well. That leads to a contradiction because you can't have it where it satisfies all three of the properties, but also fails to satisfy all three of the properties. Which is, like I said, at least one of these doesn't hold. That's the game I'm going to try playing. So, here we go. So remember, our game plan is to show that at least one of those has to fail simultaneously while I assume that all three of those properties hold. If that's the case, then we get a contradiction, because you can't have both of those things at the same time, right? You can't get all three of the properties we originally listed over there while one of them failing at the exact same time, right? It's nonsense. It's nonsense. So, here we go. I'm getting really excited here. Since the length of xy is at least the pumping length, observe that xy consists solely of zeros. Right? Notice that the length of this string is 2p, 2 times the pumping length. But the first part, the first p symbols are all zeros. By that condition over there, that means xy is all zeros. So that's one thing I'll mention as an aside, and I'll talk much more about this next time, is how we pick this string plays a very big role of how we proceed in our argument. This is the main observation that will get us to our next step. So since this is at least p, observe that xy consists of all zeros. So what does that mean? Well, if I also know that y, at least under our assumption that it's regular, it has to be that y is non-empty, right? So y actually consists of at least one symbol. So this is how we're going to exploit this. So check this out. However, the the length of y is at least 1. Remember, it's non-empty. It's a non-empty string, right? So, by the third property, I should be able to just simply consider when k is something, right? Now, remember, if that property has to hold, it has to hold for all k's greater or equal to 1. Greater or equal to 0, sorry. I'm getting really just hyped up about this. So, let's look at what happens if I consider x, y to the 0, z. What does that look like then? What's x, y to the 0, z? So remember, when I raise something to the power of 0, when I talk about a string, that's the empty string. That's just the exact same thing as writing xz. So if y has at least 1 0 in it, what happens? What happens if I write down just xz? And remember, y takes away one of the zeros at least. So what would xz be a part of LEQ? It isn't. It can't be, because now there's less zeros than there are ones. So check this out. So x, y to the 0, z consists of less zeros than ones, implying x, y to the 0, z isn't in LEQ, which is a contradiction. I'm going to just cram it in the corner here just for dramatic purposes. It's down there. It says contradiction. It's sort of melting into the into my dolphin friend over here. And that concludes the proof. Do you notice how I was able to establish a string that should be satisfied by the third property, that should be in LEQ, but I've also shown you that there exists one by picking an appropriate k value among the ones that are supposedly supposed to work. I show you that it actually can't be in the language. So that string can't be in it and also not in it at the exact same time. That's a contradiction. So meaning that our assumption that LEQ is regular is wrong, right? It has to be not regular.